Picture a standard heavy-duty pickup truck parked in a driveway. It's a rugged machine, built to haul about 1 ton of cargo without breaking a sweat. Now, imagine a vehicle so massive that it could carry 400 of those pickup trucks at the same time in its bed. This isn't a scene from a science fiction movie. It's the daily reality of a modern mining dump truck. These mechanical behemoths represent the pinnacle of heavy machinery, designed to perform tasks that seem physically impossible. Take the Caterpillar 797F, for example. When fully loaded, this monster weighs more than 620 tons. To put that into perspective, that is heavier than a fully fueled Boeing 747 airliner. It generates a staggering 4,000 horsepower, yet despite that incredible power, it won't be winning any drag races. It moves at roughly highway speeds, which feels incredibly slow for a machine with several thousand horsepower under the hood. This leads to a fundamental question that keeps engineers and economists awake at night. If these machines are so incredibly expensive to build, difficult for operators to navigate, and almost impossible to transport from the factory to the mine site, why do mining companies keep pushing the limits of physics to make them even bigger? You might think the answer is just to carry more rock, but the truth is far more complex. In fact, making a truck too large can actually backfire and make a multi-billion-dollar mine less profitable. To comprehend why these machines exist, you must first comprehend their size. Imagine standing next to a single ultra-class transport truck tire. You're shorter than the tire, likely half its height. These tires are usually 4 meters tall. A fleet of family sedans would fit underneath the truck's belly, protected by the large steel chassis. High above the earth, the operator's cab feels like a small office building's 2nd or 3rd story. A driver must ascend industrial staircases that seem more like oil rigs than vehicles to get in the driver's seat. Once inside, the view is stunning yet unnerving. The truck's height and large hood block the driver's view for dozens of feet. This engineering craziness is also evident in the Komatsu 982E5. It can carry 400 short tons. The machine weighs over 1 million pounds when loaded with copper ore or gold-bearing rock. 3,500 horsepower comes from an 18-cylinder diesel engine. These trucks have massive fuel tanks and cooling systems that can control a warehouse's temperature. The odd part is that practically every one of these huge components exists for one basic reason that governs the mining sector: because of tonnage costs. Large-scale mining production isn't measured by truck speed or paint shine. Even business truck counts don't measure it. The cost of transporting 1 ton of material from a pit to a processing plant is all that matters. Mining requires extensive logistics. Companies must move millions of tons of waste rock to find a few grams of gold or pounds of copper. If they can cut rock transport expenses by a few cents per ton, they might make millions throughout the mine's lifetime. Ultra-class cargo truck maths is evident. Consider Hall cycle equation. 40 loaded trips with 100-ton trucks are needed to move 4,000 tons of rock. This means 40 drivers, motors, tires, and cars on narrow mine roads. A 400-ton mining dump truck needs 10 trips. Reducing cycles drastically cuts manpower and fuel costs. Reduced mine traffic improves safety and efficiency. Caterpillar and other manufacturers developed these trucks to lower cost per ton. A truck cannot be enlarged forever without affecting the ecosystem. Another massive machine must fill a ton of rock before a vehicle can move it. Excavators and mining trucks always match. A significant mining engineering phrase is pass match. Buying the world's largest truck and a small excavator will idle for 20 minutes while the shovel fills the bed. That multi-million-dollar truck spends money while idling. To avoid this, Mines use ultra-class vehicles with large hydraulic or rope shovels. The goal is 3 to 5 bucket passes to fill the truck. The Komatsu PC9000 excavator operates with big trucks. This shovel can move 80 tons in one pass. It can load a 400-ton Class 980E truck in 5 passes in under 150 seconds under optimal conditions. Looping requires the fleet to travel this fast. The truck's structural problem would smash any large gear if those 80-ton loads start falling in. An excavator dropping 80 tons of jagged rock into a truck bed from several meters above is rough. A crash sends shockwaves through the car. These trucks can endure thousands of knocks for decades. Mine dump trucks use heat-treated alloy steel instead of thin sheet metal like semi-trucks. The frames are flexible for uneven mine roads, but rigid for the heavy vertical load. Dump bodies often have replaceable liners. Liner protects main structure from carried abrasive pebbles. Light coal trucks need a larger volume, whereas heavy iron ore trucks need a smaller, more robust structure. Komatsu prevents pressure-induced frame cracking using comprehensive computer modeling and full-scale dynamic testing. The massive pivot pins, frame, suspension, and tires receive rock energy from the body. Tires are perhaps the most specialized part. They're huge physically, not just visually. The truck's huge tires spread its weight. Due to overpressure, smaller tires would sink the truck on compacted dirt roads. Due to its large diameter, the truck can roll over rocks and potholes that would stop a smaller vehicle. However, tires are mining's biggest challenge. Heat comes from truck tire flexing. Driving too fast or carrying too much weight over a long distance can melt a truck's tires. Graders reduce tire temperatures and speed up transport routes, costing mines millions. Over 32 tons can be in 63-inch Komatsu 980E rims. Tires cost tens of thousands and are managed carefully. These cars don't maximize speed with thousands of horsepower, used for torque or pulling force. Imagine a truck exiting a deep, open pit mine. 400 tons of rock are transported several miles up a 10% hill. Overcoming gravity and road rolling resistance demands immense power. These engines must power massive hydraulic pumps and cooling fans in thin air at high elevations. Caterpillar 797F's 20-cylinder, quad-turbocharged engine meets these criteria. This keeps the truck at 60 km/h while loaded. Maintain consistency and reliability over speed. But transferring the load is only half the battle. Engineering a million-pound truck to stop downhill is more harder. Traditional friction brakes like your cars would catch fire in seconds due to excessive heat. Ultra-class trucks have advanced retarding systems. Many versions include oil-cooled disc brakes that dissipate massive thermal energy. Electric drive trucks' wheel motors generate power when traveling downhill. Electromagnetic resistance slows the vehicle, and enormous resistor grids on the side dissipate the electricity. The car can safely descend steep ramps without wearing out the mechanical brakes. These reliable devices can precisely hold a fully laden truck at a crawl on a steep drop. You might question why we don't develop 1,000-ton trucks with all these technical benefits. This is when scale economics fail. When is bigger no longer better? As trucks get wider, mine haul roads must get wider. Making a road wider in a deep pit, mine requires excavating millions of tons of waste rock. This can exceed the savings from a larger truck. A larger vehicle needs larger maintenance shops, cranes to hoist parts, and more expensive spare parts. A 400-ton truck breakdown eliminates a huge portion of your production capability. Sometimes a smaller fleet of trucks is more efficient due to flexibility. The best vehicle is the largest the mine's infrastructure can support. Beyond the machine, these trucks are part of a large, clandestine manufacturing. Advanced dispatch software tracks every ultra-class haul truck in a contemporary mine. The driver is told which shovel to use and which route to avoid traffic by this technology. Truck sensors check the payload in real time to prevent underloading or overloading. Trucks have radar and video systems to inform drivers of smaller cars in their wide blind areas. Some mines use fully autonomous hauling, where trucks travel without cab operators. Caterpillar and Komatsu have optimized their production chains to move mountains economically, and the truck is just one part. Because of their massive workload, mining dump trucks are huge. These trucks aren't merely bigger highway trucks. Mobile, highly specialized industrial plants. Every extra meter of height, ton of steel in the frame, and gallon of fuel burnt is estimated to lower cost per ton. They exist because the world needs minerals and metals in amounts smaller machines can't handle. The immensity of a machine that makes a car look like a toy isn't for show. It's a well-planned solution to the harsh economics of moving the earth, when saving a few pennies on a ton of rock can mean the difference between failure and multi-billion-dollar success. These titans built our modern world one 400-ton cargo at a time.